Good morning, good afternoon, everyone, whichever it is. We have done problems like this a lot in the past. You should know how to do this. Go ahead and solve this problem for me, please. Simplify as much as possible. There are a lot of different ways to attack this problem. The most common, maybe the most common, is to say 64 is 8 times 8. 8 then breaks down to 2 times 4. 2 is prime. 4 is then 2 times 2. Those are both prime. This 8 breaks into 2 times 2 times 2, which are all prime also. And this little 3 right here, that tells us that we are looking for sets of 3. I have one set of 3 here, so a 2 will pop out to represent that set of 3 2s. Then I have another set of 3 here, so a 2 is going to pop out to represent that set of 3 2s. And then looking at the x to the 4s, I'm asking myself, how many sets of 3 do I have when I have x to the 4th power? I've got one set of 3 with then 1 left over. Don't forget the index. Your final answer should be 4x times the cube root of x. Try this one. The 4th root of 5 to the 9th, x to the 5, z to the 12. Looking at 5 to the 9, I've got 2 sets of 4. The index is 4, so I've got 2 sets of 4 there. So a 5 pops out, but there would actually be 2 of them, and there would be 1 left over that stays under the radical. And then x to the 5, I've got 1 set of 4 with 1 left over. Z to the 12, I've got 3 sets of 4 there. Your final answer would be 25x z cubed times the 4th root of 5x. Try this one more. The cube root of 10 to the 5, x, y to the 15, z to the 10. Simplify as much as possible, please. All right, we should have, looking at the first term, how many sets of 3 do we have? We've got 1 set of 3. We would have 2 10s left over. Looking at x, we have no sets of 3, so it's just going to stay under the radical. Y to the 15, I've got 5 sets of 3. Z to the 10, I have 3 sets of 3 with 1 left over. Your final answer would be 10 y to the 5 z cubed times the cube root of 100x times z. All right, so as we've said a few times already, if you're looking at a problem like, say, the cube root of x squared, the little number that sits on the shelf there, that is called the index, and the index tells you how many of the same number you need to pull that number out. And this x to the 2nd power, that 2, that's the power. As you learned back in Algebra 1, Algebra 2, every radical can be written as a fractional exponent, or instead of fractional, we can call it a rational exponent, where you have x to the 2/3, where the number on top, that's the power. It's on top because it's powerful, and the number on bottom, that is the index. So again, when you have a base with an exponent, something like, say, x to the 4/3, that can be written as a radical by this little guy swinging around. It becomes the cube root of x to the 4th, and then we can simplify as much as possible and get x times the cube root of x. For this type of problem, I've always imagined that little number on the bottom there. I've imagined him to be a little monkey, and he's holding onto a branch, and then the monkey swings around and lands on another branch over here. So here's the little monkey, and he swings around, and it becomes the cube root of x to the 4th. But that's just how my brain works. So now, try for me, please, to simplify as much as possible 25 to the 3/2. Simplify as much as you can. I start by finding the little monkey, and the little monkey swings around and lands on the shelf, so it's the square root of 25 cubed. I've got 2 25s in there, so 1 25 is going to pop out, and then I'm going to be left with 1 25 on the inside. I'm not done yet because rad 25 is 5, and then we have 25 times 5, which equals 125. Let's try again. Simplify as much as possible, please. 25 to the 2/3. The little monkey in the tree swings around, lands on another branch, so I have the cube root of 25 squared 25 squared, I could multiply that together and get 625, but a better way maybe is to say that that is simply 25 times 25, and that becomes then 5 times 5 and 5 times 5. We're looking for sets of 3. I've got one set of 3 with 1 left over, so you should end up with a 5 cube root of 5. When you have numbers multiplied under a radical like that, you don't actually have to multiply them together, because remember, all we're trying to do is break them down, break the product down to its primes. So you don't want to multiply to then have to just break it down from there. So what could we write instead of the square root of x? How could we write that with a rational exponent? Well, you don't see it, but the power on the x is a 1. And if you don't see an index, then the index is a 2. So the little monkey can swing back around, and we get x to the 1/2. Again, the power's on top because it's powerful. The index is on the bottom. Every number is made up of 2 parts. There's the big guy on the bottom. This is the base. And then this guy sitting on the top, that is the exponent. And then the exponent has the index and the power, as we've talked about. So looking back, the big guy is the base. Then we have the exponent. The big guy is the base. Then we have the exponent. I've probably told you at this point, but my sister was a cheerleader in high school, and she was a flyer. She was one of the little ones that they would throw up in the air. And the girls on the bottom who were doing the catching and the throwing, they were called the bases. So the flyers would be up on the bases. So the bases are the ones that hold up the flyers. And same with math. The bases are the numbers that hold up the exponents. So let's go back to this problem right here. We found this problem, 25 to the 3/2 equaled 125. And I'm going to write that down at the bottom here. 25 to the 3/2 equals 125. This is just basic exponential notation, but this notation can be written in a different, very much fancier way. And to write this in a new, fancy way, we need what is basically a fancy mathematical code word. The code word that we're going to use is, it means the exponent. And the fancy code word that we're going to use for the exponent is log. The full word, as you've heard before, is logarithm. And the fancy new way to write this basic exponential notation is log base 25 of 125 equals 3/2. We'll break this down in just a second, but I'll read it across one more time. This reads log base 25 of 125 equals 3/2. So knowing that the word log simply means the exponent, if I want to read this straight across and use my code word, I can say the exponent that the base 25, see how 25 is written lower than everything else? That means it's a base. The exponent that the base 25, then we raise up, must be raised to get 125 is 3/2. So again, that's the exponent that the base 25 must be raised to get 125 is 3/2. I'll read that one more time. The exponent that the base 25 must be raised to get 125 is 3/2. And while that is accurate, it's kind of a little bit clunky to work through. So when I work with logs, I don't actually think of that sentence. I think of an actual log that you might find at a park or maybe floating in a lake somewhere. So stick with me here. When you think of a log, picture a really big, kind of cute lake. Yeah, kind of like that. Now, in this lake, floating in the lake, there's a log. Maybe it's a branch that's fallen off a tree, but there's a log floating in the lake. Just like that. Now this log is the actual log from our problem, so I'm going to go ahead and label it log. Now also in this lake, there's a little ducky, and this little ducky swims around all happy. Ducky is the base. So I'm going to go ahead and write a 25 on the ducky. Now imagine in this lake too, some lily pads and maybe some leaves have fallen off the trees. Something sort of like this maybe. So we've got a log, we've got a ducky. The lily pad is the number that we're raising to, which in this case is 125. And then the leaf is the 3/2. So in this case, our ducky is finding himself in this big, beautiful lake, but he's getting a little claustrophobic, stuck between this log and this lily pad. And he looks over and he sees lots of room in the lake, and so he decides to duck dive under and come up on the other side. But when he does, unfortunately, he comes up with a little leaf on his head, the silly little ducky. So our ducky here dives under the lily pad and comes up on the other side, but he ends up with a little leaf on his head. Now, when he dives under, the log, maybe a gust of wind comes up or the ducky kicked it or something, the log floats away. And what you see here is 125 equals, remember the ducky was the 25, 125 equals 25 to the 3/2. Which is exactly what this converts into. 25 to the 3/2 equals 125. We have converted from logarithmic notation to exponential notation. Now, let's say we need to convert from exponential notation back to logarithmic notation. The ducky's not too excited about having a leaf on his head, and he looks back on the other side of the lily pad and he realizes there's a big open lake over there. And so the ducky decides that he's going to duck dive back under, and he comes up on the other side, but wouldn't you know it, our poor ducky, right when he does that, the log comes floating back over and makes him claustrophobic again. Let's look at this again. Let's say we were told log base 2 of 8 equals 3. Imagine the little ducky swimming in the lake. We've got a log next to him. Here's our little ducky. He's feeling a little tight in that space, so he duck dives under. The log floats away. We end up with 8 equals 2 to the 3. 3 is the little leaf on the head. Now we're in exponential notation, and if we want to convert back to logarithmic notation, find the ducky. The ducky has the leaf on his head, and he duck dives back under, but the log floats back over. Log base 2 of 8 equals 3. Let's try another. Let's look at log base 4 of 16 equals 2. We're in logarithmic notation. Try to convert to exponential notation. We find the little ducky. The ducky dives under. The log floats away. We get 16 equals 4 to the 2. Now, if we convert from exponential notation back to logarithmic notation, we just find the ducky. I always want the ducky on the right-hand side of the equation. The ducky dives back under. The log floats back over. We get log base 4 of 16 equals 2. One more here. Let's go with log base 10 of 1,000 equals 3. Convert this to exponential notation. The ducky dives under. We get 1,000 equals 10 to the 3. Now what I wrote here, this log base 10 is called the common log. And what I wrote, you actually won't see all that often, a log base 10, because since it's so common, they just don't write the base usually. A log base 10 usually appears without its base. If you ever see a log without a base, that is the common log, and its base is 10, and you can go ahead and write in a base of 10 if you want. So now let's take a look at 3 more logs and convert each one to exponential notation. You'll notice the last log in green doesn't have an equals anything. When a log doesn't have an equals anything, typically they're asking you to simplify. And if they're asking you to simplify, you can say, well, it equals something, and you can bring in your own equals x. Go ahead and convert each of these to exponential notation. The little ducky ducks under, the log floats away. I get 4 equals x to the 1/3. The little ducky ducks under, the log floats away, and I get x equals 4 to the 5/2. Again, the ducky ducks under, the log floats away, I get 27 equals 9 to the x. These 3 problems represent the 3 basic log problems that you'll face. The x takes up the 3 different positions that it could possibly take in a log problem. It's the base, it's the lily pad, and it's the leaf. So for each of these questions, we're going to be solving for x. We're going to be solving for x. And our simplify problem, once we brought in the x, it becomes a solve for x problem. So at the beginning here, this first blue problem, we've got 4 equals x to the 1/3. When we're trying to solve for x, we're trying to get x equals something. That's x to the first power equals something. But right now we have x to the 1/3 power. So what can we raise both sides to so that when we multiply our exponents, we get x to the first power? If we raise both sides to the third power, x to the 1/3 times 3 gives us x to the first. And so we have x to the first equals 4 to the third. We get x equals 64. Remember how exponents, when they are raised to a power, those exponents get multiplied. So let's pretend we have the situation x to the 2/5 equals 4. What could we raise both sides to get x to the first power all by itself? You could raise both sides to the 5/2 power. So now when we multiply these exponents, we get 2/5 times 5/2. We get x to the first equals 4 to the 5/2. But now we need to simplify this as much as possible. I'm going to flip this around. I get x equals 4 to the 5/2. The little 2 is a monkey. I swing them around. I get the square root of 4 to the 5th power. I'm looking for sets of 2. How many sets of 2 do I have? I've got 2 sets of 2 with 1 4 left over. That's going to be 4 squared is 16 times 2. I end up with an answer of 32. So now looking at the next problem. I've got solve log base 4 of x equals 5/2. The little ducky ducks under. I get x equals 4 to the 5/2. And at this point, oftentimes, I'll have students who go, ooh, I'm going to raise both sides to the reciprocal. But that doesn't actually help us, because by raising both sides to the reciprocal, we are losing our x to the first. No, instead, we need to simply simplify what's there. We need to solve x equals 4 to the 5/2, which we just did right down there. X equals 32. So now finally, moving on to the last problem. We have log base 9 of 27 equals x. The little ducky ducked under, and we got 9 to the x equals 27. Now let's pause this problem right here for just a second. If I have a problem where the bases are the same, I can simply cancel the bases so that the exponents are equal. Again, if I had, say, 7 to the x equals 7 to the 5, well, that would mean that x would have to be 5 in order for these problems to be equal. When the bases are the same, you can simply cancel the bases. But in this problem that we have, 27 equals 9 to the x, the bases aren't the same. Can I write 27 with a base of 9? 9 squared is 81. No, I can't write 27 with a base of 9, but is there any base you can think of that would give us 9 and 27? 3 squared makes 9, and 3 cubed makes 27, and multiplying my exponents together, I have 3 cubed equals 3 to the 2x. Now my bases are the same, so I can simply cancel away my bases. I get 3 equals 2x. I can divide by 2 and get x equals 3 over 2. Let me know if you have any questions, guys. Have a great day.